Okay, let's continue. As I was made aware of in the break, there was this mistake in the flow diagram here. So for CSMA with collision detection, there is a maximum number of times we can go through this loop here. And so it was a mistake in this statement here. So basically when k is less than k max, then we go up here because then this is true and we go another round. Otherwise we abort it. So thanks for spotting that mistake. That's actually not in the book, it's myself that put that in, so I cannot blame the author in this case. All right, so now we have talked about this type of math methods, medium access control, which is sometimes called random access, where we basically have loose coordination between the stations who would like to share the medium, and we use random backoff times, we use ACK or collision detection to figure out when there are collisions, and then adapt to this. There is another set of medium access control methods which are more organized, that before we actually start to transmit data, we self-organize on how to send this data. So you can think of it maybe as if we had like a formal meeting, I would have a piece of paper, and those who would like to talk, I have a speakers list, and then we go in the order of the speaker list. We do the speaker list before we even start to talk, right? So this is called controlled access, where there is a sort of like a setup phase before actually the communication goes on. So there is a set of these. Okay, so we talk about controlled access here. There are a family of these called reservation protocols or reservation systems, and they could be centralized or decentralized. Centralized is maybe the most common one, is when we have a special node or a controller, a central unit that accepts requests to send from stations and then issue grants for transmission. So we can think of this maybe as a, like in 4G or something like that. If this user equipment, this phone, would like to transmit something, it first contacts the base station and says, hey, I have some data to transmit, this is okay. And then the base station says, yes, you can, right? And here's when and where you should send it, like at what frequency, at what time, with what modulation format, and all these things, right? And it's yeah. So that's an example of this in practice. So if we started with the very, very simplest thing we can think of when it comes to reservation, we had this notion about cycles and reservation intervals and data intervals. So transmissions are organized in cycles, and these cycles could be potentially of different lengths. And a cycle, if we take the cycle here in the middle, it starts with this peach reservation time, and then there is a couple of data frames. So there are 3 blue data frames after this reservation. Then there is another reservation time, and then it happens to be 1, 2, 3, 4, 5 data frames after that. And then there is another reservation, and so forth. So the reservation here is divided into a number of mini slots, 1, 2, 3, up to capital N, where capital N is the number of users. So in this, we organize whether user number 1 has some data to transmit, whether user number 2 has some data to transmit, and so forth. So in this case, for instance, user number 1, if user number 1 has some data to transmit, it says, hey, I'm number 1, I would like to transmit. And then everybody knows that the first data frame that follows is the data frame from number 1. So if number 1 and number 3 and say number n said, okay, we would like to transmit, then the data frame the first data frame comes from user number 1, second one comes from number 3, and the fourth one happens to come from capital N in this case. Right? And then there is a new cycle, and then, for instance, maybe in that cycle, user number 1, 2, 4, and N again said that they would like to transmit. Then we know the order of transmission here. It would be then the first one would be still from user number 1 in this case. Number 2 would be from number 2. The third one would be from number 4. And then it would be okay, so maybe this didn't work out in this case. The last one should be N here. So maybe this is from N minus 1 and this is from N, like this. Okay, and then there is another round of reservations. So questions on the general setup here? Okay, and the idea is, of course, that the reservation time, the time it takes to reserve this, is much shorter than the actual data frames. Otherwise, this doesn't make much sense, right? There, of course, there is not a lot of data saying, okay, I'm number 1, I have data to transmit. Maybe this is like 4 bits or something like that, or 16 bits or something like that. Well, the data frame could be an IP packet, which is 12,000 bits or something like that. So there are two main methods here, centralized or distributed. And centralized is when we have a centralized controller. Distributed is when each station listens to the rest. Okay, so centralized controller listens to the reservations, decides the order of transmission, and then issues grants to transmit. A distributed is when each station listens to the reservation transmissions and then determines its transmission slot. Okay. Now, there are pros and cons with both of these. One obvious thing is that in the centralized method, if the centralized node dies, everything dies. In the distributed, there is a problem where different nodes might not hear the reservation slots very well if they're further away, assuming that the central controller is in the middle. It has an easier time to hear every transmission. And if there is then two nodes who miss these reservation intervals, then there could be collisions in this case. Okay. We will return to a few issues here. So, but let's do a few calculations here. So suppose we have a mini slot duration which is some factor nu times TF, where TF is the data frame and nu is some number less than 1. So maybe nu is like a very small number, say 0.01 or something like that. I mean, for this to be efficient. Or maybe it's like something like that, say, for example. Then, if we assume that the propagation delays are negligible compared with nu times TF, then there is no need for guard intervals here, so we ignore those. Then if all end users have data to transmit, what is that it gives us the maximum row we can support with this system. And the maximum row, what is that? Well, it's how much data we transmit per frame duration. So basically we can count the time it takes to transmit data in a cycle divided by the cycle duration. This tells us how much of the medium we are using for data in relationship to the total time we use. So for instance, in this case, this is the time reserved for reservation. So this is useless from a data perspective, while this time here is when data is actually transmitted. Okay. So we want the blue part to be a significant part of the peach one, otherwise we will be in trouble. Okay, so what is the data part? Well, it is the blue part, which is n times TF. We transmit n frames, 1 per user, TF, seconds per frame. So it's n times TF is the data portion, is part of the blue part there. And then the total part consists of the blue part and the reservation part, which is n times the mini slot time, which is n times nu times TF. And if we divide by n and tf in the denominator and numerator, the end result is that the rho max is 1 over 1 plus nu. Okay. And here we see that in this example, when nu is very small, we see that we are a number very, very close to 1, right? Which is the best we can ever hope for, right? Rho max can never exceed 1. So in such a situation with the very small nu, when we have all users are actually using the channel and the propagation delays are negligible compared to the mini slot time, then this is a very good scheme, right? If it's not like that, maybe the scheme is not great. So the first thing we can see that efficiency drops when only m out of n users are using the channel. So say that we have 1,000 users being attached to the network, but at any given point in time, only 10 of these actually have data to transmit, right? That could very well be the case, right? Right now we have maybe 30 phones in this room. All of them are attached to the network, but maybe not all of them need the network at this point in time. That could very well be the case, right? So what happens then? Well, again, we can calculate rho, which is m times tf. This is again, the data part. And then we divide with the data part and the time it takes to do the reservation. And we see here that we need 1 mini slot per potential user, right? So we have n users, but we only transmitting m data packets per cycle. And then when doing the calculations, we see it's 1 over 1 plus nu times this factor n times m. Okay, so what was in this case, n over m is what? 100, right? Then, okay, so this did not fully compensate for the low value of this, but you see it's effectively we get another nu. Okay, so if then say that we had m equals 1, then n over m is equal to 1,000, and then nu times n over m is equal to 1, and then we see that efficiency dropped to 1/2. Right? So this is a bad situation for reservation interval when we have many users, but only a few of them are transmitting at any given cycle. We can counteract that a little bit. If these users have a lot of data to transmit, then we can maybe reserve just not only 1 slot, but say up to k slots per user in cycle. So then we get a situation where the data portion is m, because we have m users, we have k slots per user, and there's tf seconds per user. So the blue part would be m times k times tf. That blue part we see down here, and then the reservation interval is the same. It is still n times nu times tf. And if we do some calculations, we see that the result is 1 over 1 plus nu n divided by k times m. So by making k large, we can compensate for the low activity level of the users. So this is one way to counteract that. So again, if then k happens to be 1,000 again, then we are back to where we started. Really. So any questions on these modifications to the basic scheme and the efficiency of those? So basically one can say that with control access, if the penalty of doing the actual reservations is low, then these schemes are very efficient. If the penalty is not low, then these systems are not efficient. And yeah. So one thing that we have not discussed here, and that's going back to this, is that here, this is a medium access control system, right? So what we want to do is to control access to the medium, And we do that by reservation interval here, where we reserve the medium for future use. But this is tail biting, right? In the sense that how do we organize this access of the mini slots to the users? So we need a max scheme for the reservation part in order to implement the max scheme for the blue part. Right? We use the medium to do coordination. As soon as we use the medium, we need a max scheme. Right? So what has actually been gained here? Well, the idea is that either we have a predefined channelization that we will talk about in a short while, that we actually have these time slots, we have synchronized stations, we know when the stations can start and so forth, then it's not such a big of a problem. But there is a problem when only a small fraction of all the potential users have data to transmit. So when m is much less than n, so in this case say that m is equal to 10 and we have n equals 1000, for instance. Then we are in a situation where we have many reservation slots, mini slots, but not all of them are ever used, right? Because only 10 out of those 1000 slots will indicate that data is ready to be transmitted. Okay, so what we do then is the main idea is that we use L mini slots rather than N mini slots. Okay, so going back here, we need here capital N slots, where capital N is the number of users. But if only a few of these users will ever indicate its willingness to transmit something, how about if we reserve less than capital N slots here? Let's reserve L slots here, meaning that it's not possible for everyone to make a reservation. But that's okay, because not everyone will make a reservation. Okay, so the idea then is that we use L slots, which is less than N for reservation. And then since L must be larger than M, however, because M is the expected number of users that will ask for a data slot. So L must be larger than M. As a matter of fact, it might be substantially larger than M. And why is that? It's because the random access MAC that we use for assigning these L reservation slots have a maximum normalized throughput, which is less than 1. So for instance, to make this clear, suppose we use slotted ALOA in the reservation part. Okay, so we use a random access thing to do the reservation, and we have L slots. Then we know that in the best case, we can schedule L over E, L over 2.7 stations, because the slotted ALOA maximum normalized throughput is 1 over E. Okay, so which means that L must be chosen to be M times 2.7 in this case, which is of course greater than M, but this is still beneficial if this is much less than N. So that the premise is that N is much larger than M, and if L is such that M times 3, or basically M times 2.7 is equal to L, is still much less than N, then this is a good scheme. If not the case, then it's not a good scheme. And then if that is the case, that this is the maximum supported load of such a reservation scheme is again the data part. Okay, so we can schedule yeah, exactly. So from this it follows that M, the number of users that we can schedule, is L divided by 2.7, or actually L divided by E. Okay, so we schedule L over E users. All of them transmit the frame on length TF. So the data part is L over E times TF. And then the reservation part is L times slots, L mini slots. So it's L times nu times TF. And if we divide through, we get this. Questions on this? Okay, so that about reservation schemes. So just to summarize what we have been talking about. A reservation scheme organizes data transmission in cycles. We have a reservation interval and then a data interval. In the reservation interval, we need to have mini slots. Okay. Access to these mini slots require also medium access control. Either we use it like this, which is sort of like TDMA, where each user has a time slot, it's predefined, users are synchronized and everything as well, or we use a random access method for accessing these slots. These are the two main options. Okay. Now, another idea about controlled access is what's known as polling. And here we have a central controller that is asking users whether they have data to transmit or not, and informs users of if there is data that is transmitted to them. So we can think of it like this, that we have a master, a primary node here, which controls access to several stations, here A and B. Now, if the primary computer has some data that needs to be transmitted to B, it sends a special message to B saying, okay, I would like to select you for transmission. Then if B is ready to receive some data, it sends an acknowledgement back saying, okay, I'm ready, please send me the data you would like to send. And then the data is transmitted to B, and then there is an acknowledgement for that data. So the data exchange from the primary to one of the stations consists of this first handshake to figure out whether are you ready to receive some data, and then actually some data transmission. Okay. So B here and A are not will know by listening to the channel for their selection message that they have data to be that they should get. Okay. So this is roughly how LTE works, where the base stations pings the mobile and says, okay, I have some data for you, are you ready to receive this? Right? And then the station says, yeah, I'm ready, and then the data comes. Same wise goes the other way around, where say the station then talks to A and say, okay, do you have any data to transmit? And then A says, no, I don't have anything for the moment. Okay, and then the primary or master then talks to B and says, hey, do you have any data? And then B says, yeah, I have some data, here it is. And then there is an acknowledgement for that data. So that's another exchange of data. So these are called polling. Maybe this is what is technically what is polling, where the primary basically goes around among its stations and then asks them if they have data to transmit. Any questions on this? No? Then of course there are variations of this where this polling message goes out to A and maybe B, say, and maybe the data which is transmitted is not intended for the primary user. It could be for A. It could actually be for anybody who's on this shared medium, right? So it doesn't necessarily have to go to the primary. And